Hello everyone, I've been instigated in the comments recently to talk about the Constellation program and the Ares 5 rocket in particular, and this gives me opportunity to introduce my own Cassay rocket again, because the Cassay rocket is meant to be a version of the Ares 5, an improvement on the Ares 5, and reflective of what I think is wrong about the Ares 5. And the first thing is we need to replace the engines. So we have 5 RS-68s here. These are from the Delta IV rocket. And if you've ever seen a Delta IV rocket launch, it blasts the side of the rocket for reasons I still don't quite understand. I mean, I know technically what it's doing, but I don't know why it needs to do it when no other rocket produces flames like this. They thought it'd be alright because there's only one engine on each core of the Delta IV, so it's not harming anything when it does it. But then they decided to put 5 of them together, and it turns out that the fact that it torches the side of the rocket produces thermal issues for the neighboring engines, and they should have probably realized that when they proposed this. I mean, apart from everything else, there's these pipes that are sticking out that are sticking out because they don't want to blast the nozzle with all their heat, all the stuff coming out of the gas generator and such. But that's really inconvenient for the other engines. I mean, when you have 5 of them producing all this stuff, well, they can't be like that. Basically, the engines would need to be redesigned. And they discovered that the engines need to be redesigned, but they probably should have realized that if they just watched a Delta IV launch at some point. So there's a certain lack of foresight that comes into the Ares 5, and there's also some excess of foresight, if you will. What we have here to begin with is an 8.4 meter core, which is the same as SLS and the same as my Kasei rocket. So all rockets have the same core diameter here. And if we take off the boosters, you'll notice that just with the RS-68s, it can basically lift off with the thrust that it has. So the boosters, and there's the first objection, do we really want the SRBs is a huge question. And my own personal answer was, I don't want the SRBs. The thing about the SRBs is they're handy if you're only going to put like one engine on the core. So there's like the Ariane 5, Ariane 6, or still have an underpowered core like on the H2 or H3 rockets from Japan. Those all have solid rocket boosters because the core can't lift off the ground on its own. But this can. So then maybe you could have better performance boosters instead of these. And maybe they were thinking about that with like F1 boosters and stuff like that. This is the excess of foresight that I'm talking about. So we can basically replace the boosters with something with less thrust but more performance. Now, why do I object to the SRBs? Well, if you can launch your rocket without the SRBs, you can use smaller facilities to launch the rocket, or given the same facility, you can get more payload to orbit without the SRBs, because the SRBs create a lot of noise. They have a lot of thrust, but they're not very efficient. So you basically get less payload to orbit for the amount of infrastructure that you have. So if your pad can accommodate a certain amount of noise, a certain amount of mass on the pad and stuff like that, then they're not the best choice if you don't need all that thrust to help your rocket. So that's one objection. And the best option, if you are infrastructure constrained, like on pad 39A or B, is to have just hydrolocks, straight hydrolocks. Of course, it's complicated, but you're already a hydrolocks rocket, so there is that. But why do they have the core capable of lifting off like this? Why does it have so much thrust down there? And for that, we have to take a look at the upper stage and the payload. Right now, the payload I have on here is 120 tons, but it's rated for 140 tons to low Earth orbit. So it's trying to match Saturn V. So we can boost this up 140 tons. But then we certainly don't have enough delta V to get there, even with the boosters. Let me get the boosters back on, actually. 120 tons is already pushing it considering the thrust weight ratio of the second stage, and that's the key here. So we're going to increase this to the rated capacity of 140 tons to low Earth orbit, and it's clear that we can't just have one J2 or one J2X on this second stage. We'll need two. But if you've got two engines like this is overkill for transferring to the moon, right? So you're going to have to make this bigger, and you're getting a whopping 2,000 kilonewtons, 2,600 kilonewtons from your potential Earth departure stage. And that's to accommodate a low Earth orbit payload capacity of 140 tons. And actually, we still need to make this a little bit bigger. So at this point, we have the 9,500 meters per second to get to low Earth orbit. We have a decent amount of thrust weight ratio. The burn time's not a problem, and we're using two J2Xs up there. So, but then the rocket sort of has an identity crisis, right? It's designed for this 140-ton payload to low Earth orbit, but then you're gonna be trying to maneuver this very heavy stage with two J2Xs to do the transfer to the moon. And in that case, it's not going to have the 140 tons potentially, unless it's got another stage up there, which is what I'm getting at. It's going to have some small payload. And so let's say we've got this small payload here. The ultimate thrust weight ratio isn't going to be too bad. And what this ends up getting is about the same payload capacity to the moon as Saturn V. So it's pretty clear what they were aiming for here. So that's about a lunar delta V, and they're trying to get the same sort of payload capacity to the moon as Saturn V, 48 tons, and that's what they've got. So in that respect, it's fairly good. However, I just have this thing where, okay, we've made this huge stage now, and we're going to try to have it do the work. Its engines aren't particularly efficient. We could get 460 out of a stage instead of 448. They're relatively heavy, and we don't need a thrust weight ratio in space. So we've got all that as an issue. And then we can still get off the ground without the SRBs. Of course, we won't have enough delta V like this to actually get to the moon, but notice that if the payload was capable of adding 900 meters per second to get to the moon, that'd be enough. So, and the rocket is half the mass as the SRB version. So it can get off the ground with 11,676 meters per second with half the mass, and with the SRBs, it's 3,000 there. Well, though we can cut this down back to the 48-ton lunar payload. So something's screwy here. So we would just need a little bit from the payload in order to get over to the moon, like this. And what I decided to do with the Cassay rocket is just design a low Earth orbit system, and then put some other third stage as part of the payload. So as part of the 140 tons, we would have a third stage. And really, the Cassay can do more than 140 tons low Earth orbit when it has boosters. So the net effect is that given a pad that can accommodate a 3,000-ton rocket and all the noise of all the thrust, if we switch out the boosters here for methane boosters instead, we get a better deal. Let's take a look at the Cassay rocket. So we still have 5 engines at the bottom, but instead of having the RS-68s, we have my own hypothetical ED9s, which were meant to be somewhat more limited M1 engines. And we get 4,000 kilonewtons, so they're a little bit souped up, and they're souped up because they are stage combustion engines at this point. Previously, I had the ED6 engines on, and they were still gas generator like the RS-68s, but instead of having the pipes stick out and blowing all the gas generator exhaust out, they dumped it back into the nozzle the way the F1 engine and M1 engine would have. We have these reasonably sized engines, and 5 of them, they do get a little bit more thrust than the RS-68s. The RS-68s get 3,380. So these are a little bit more powerful, and they're more efficient because they're staged combustion, and they're also lighter because they're staged combustion. They have a higher chamber pressure, so physically, for the given amount of thrust, they're physically smaller. And they'll get better performance like that too. So they're not losing the stuff from the gas generator exhaust. So we've got staged combustion engines there, which give us a good boost. And since we're going to be focusing on lower Earth orbit capacity, and we're only doing 2 stages here, we're not taking a look at our 3rd stage yet. We've got just one of those ED9 engines in a vacuum configuration with a vacuum nozzle on this stage, and it gets 450. So then we've got a pretty nice deal. Now the 450 is not that much more than the J2X's, it's just 2 seconds of ISP more. We have more thrust, which means that we can have an even bigger stage here, and that stage is more capable to as far as getting our payload to orbit, and we have better manufacturing because we're basically pulling a SpaceX here, like with the Merlin engines and with the Raptor engines. Same idea, we're just making one line of engines and then slapping a larger nozzle on it. So we've learned that lesson, and without the boosters we can carry 95 tons to low Earth orbit. Now that's less than the Ares 5 could do without boosters, notice. So this is fairly conservative, and despite the better performance engines, part of that is because this is a heavier engine now, right? It's a 6.8 ton engine, so that's hampering us a little bit. I also made the tanks a little bit more robust than what we're doing with the Ares 5 mock-up that I made, because those were sort of light. And then we can add boosters to this. So, and normally I fly it with methane oxygen boosters, and those were the Sagitta boosters, though I've contemplated many other arrangements. But this is designed for an upper stage. And actually the upper stage that this is designed for, ultimately the one that I use most often with it, I don't have in here. Because this is overloaded install, I normally don't have the Cassay rocket in here. This is a history install with all the historical rockets, and I don't use my fictional stuff in here. But the Fuji stage is a nuclear thermal stage, so it would get very, very good performance to the moon and then be reused. So anyway, the Ares 5 rocket is not the worst thing in the world. The worst thing in the world is the Ares 1 rocket. Sort of, I mean, I feel like that was certainly the weak point in the whole thing. But certainly the biggest problem was that they picked the RS-68 engines, and then the logical thing was to replace them with the RS-25s. And ultimately what you end up getting when you change this rocket so that it's actually a rocket that's meant to deliver payloads to the moon and not low Earth orbit is SLS. So what does SLS do? Well, it takes out the RS-68s, which are problematic, and it no longer aims for the low Earth orbit capacity, so it doesn't need more engines, even though the RS-25s have less thrust. It can do with 4 engines, because it's not trying to have a core that can lift off on its own. Not that that was ever necessary with the boosters there. So the issue is that we are going to end up with upper stage that is more meant for getting to the moon, which means we need higher ISP and not as heavy an engine, and that's why you have the 4 RL-10s we see on the EUS, the Exploration Upper Stage. And that's the logic of SLS, that they're going to make a rocket that's meant for the moon. Now, it ends up having less payload capacity to the moon. And why is that? Because this can get 48 tons. So if that's an optimized rocket for the moon, why is it getting less? Well, it's getting less because it's trying to pull off this 2.5 stage thing and making it 3 stages. You need 3 stages to get to the moon. And just because you slap boosters on, it doesn't mean that you've really staged. Okay, the conceit with these Hydrolox rockets that have the SRBs is they're pretending that the core plus boosters is stage 1, and then the core without the boosters is stage 2, and then the upper stage is stage 3. Mathematically, you need the 3 stages to have an optimal high orbit capacity to either GTO or the moon. Now, what's the problem with this? Well, the problem is you didn't stage off all the mass of stage 1. You're still carrying that heavy tank there. And this is why I say the tank is relatively light, by the way. This tank really ought to be about 80 tons, and the Cassay rocket stage is 80 tons. So I'm being very kind to Ares 5 to get its 140-ton payload, but honestly, it probably couldn't do the 140-ton payload. We're being very kind to its payload capacity and its dry masses. And probably in their designs they were too. So, I mean, after all, they missed the whole thing about the RS-68, so we can assume that they made the core a little bit lighter than they ought to have. But you're not staging all the mass, and so it's not really a full stage that you're getting off now. Admittedly, the SRBs are just really, really heavy in their dry mass. These are 85.5 tons apiece dry. So that's not great. So you're staging off a lot of that, but you're not staging all of the mass of that stage. So this is still acting as stage 1 really, and then it is still acting as stage 2, and that's true of SLS as well. It's carrying that heavy core tank, and it never staged off the mass it was supposed to stage off in order to get the boost to the moon, and that's why it's more mass constrained. But also this is a lie, right? So instead of getting the conveniently low mass situation, let's try and use the sort of normal aluminum tanks to see what it really could do. What was Ares 5 really capable of? First of all, in the let's just go straight for the 2-engine configuration. I mean, I say what it was really capable of, but we're still being kind. This is now 66 tons instead of 80, so it could be worse. But right now, I've got at 9,500 meters per second without the fairings, and 116 tons to low Earth orbit. So that's getting pretty close to... it's actually less than SLS Block 1B to low Earth orbit. And if we wanted the payload capacity to the moon without any third stage, so 12,500 is what I said. Now we see that's 36 tons. So also less than SLS Block 1B. So then we see that if we get these tanks to the masses they ought to be, instead of the optimistic masses, then we get the limited capacity for Ares 5 that we would expect from a not so optimized situation for the moon, or for low Earth orbit really. The reason why we get less for low Earth orbit is because the engines just don't get as much ISP as SLS does. SLS, the RS-25s peak out at 453, even better than the ED9s on my Cassay rocket. So much better. So the Cassay rocket's somewhere in the middle of using the RS-68s and using the RS-25s, but the RS-25s are phenomenal in vacuum. So that's one reason why SLS would actually perform better than the Ares 5. The Ares 5 estimates were based on a nice, very light tank that they really wouldn't get. And that is, aside from the fact that we can't cluster the RS-68s, the main objection. So if you want to get the rated capacity for Ares 5, you can't do it really. So yep, that's the Ares 5 for you. And I felt that my Cassay rocket with its dry masses was a more legitimate thing overall, and it made better use of the stages, and it had more efficient engines. Still not as efficient as the RS-25s or the RL-10s, but yeah. the Ares 5 was a bit too optimistic in many respects. So, with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below. And I'll see you next time.